This tutorial is a continuation or discussion on forces acting in more than one direction, namely two-dimensional forces, where some of the force is acting vertically, some of it's acting horizontally. The key thing that we learned from the other lesson was if I have some generic force, it could be a tension, it could be whatever, I'll just call it T, is that if it's, in this case, directed up and to the right, that some of the force is to the right, and the rest of the force is up, such that I make a vector triangle that looks like this. And the angle that that tension makes with some reference is very, very important to determine how much of it is horizontal and how much of it is vertical. So we're going to apply this in just one more situation, and then we will turn our attention a little later on to the last situation, which is ramps, which will be a different lesson. Okay, so let's say we have a problem. So this is dynamics. Dynamics means we are not going to leave the object stationary, which was statics, the first page. Here we're trying to change what it is doing. So that's the fancy way of saying creating changes in motion with forces. So we have Stinky is trying to pull a crate right here across the floor by attaching a rope. So we have a rope like this, and he pulls at an angle from the horizontal. So that angle is 30 degrees. He pulls with a force of 120 newtons, and the angle, he says, 30. If the maximum amount of static friction is 90 newtons, will he succeed in moving the crate? Okay, so this is, if you will, a tug of war. Is there enough force to overcome whatever force holding the crate in place? So let's do a force diagram so that we can get a good handle on what's going on here. We'll do for all the forces. So the first one is we have our applied force, or I'm going to call it tension since it's attached to a rope. So we know that the tension is 120 newtons, and it acts along the rope. So we already have the arrow here. So there's our vector. Okay, what else do we have? Of course, we got gravity. So we have F of G, and it's not falling down. So there's something must be holding it up. Then the floor is helping to hold it up. There's a normal force. And you were told that there's static friction. Since we're trying to pull to the right, static friction is going to be the left. So I'm going to call that F sub F, and I'm going to put an S there for static friction, and I'm going to label this as 90 newtons. Okay, so it seems like a vague question. Will he succeed in moving the crate? So you got to be able to reason this through conceptually. What's going to allow the crate to move to the right? Well, we know it's going to be the tension. So is it okay just to say that 120 newtons is greater than 90 newtons, and therefore it will accelerate to the right? As you're thinking about this, think about what we learned the other day. Is this tension vector, if the friction vector is to the left, is a force that's up and to the right comparable? And hopefully you answer, no, it's not, because the only thing that I would do to overcome a leftward force is a rightward force. Long story short, what we want to be able to do in order to answer this question is take that tension vector and see how much of it is to the right. And then we can compare that to the force of friction. In other words, we are going to take this vector and break it up into two components. One component is going to be to the right, and I'm going to stop right here, and then I'm going to turn upwards to make a right triangle. And I'm going to call this T sub X, and I'm going to call this T sub Y. So once again, we have that vector triangle where we take a particular force that's angled and break it up into horizontal and vertical components. Okay, so now the rest is trig. I want to know, essentially, what is Tx? Well, if we apply SOHCAHTOA, we see that Tx is the adjacent side to the 30 degrees, so we should associate that with cosine. So I can say Tx equals the applied force, the tension, multiplied by the cosine of the angle. And I can also say that Ty, this component that's pulling up, so Stinky might not be trying to do this, but he's pulling up on the crate a little bit, is going to be equal to the tension times the sine of the angle. Now we can put in numbers. So this is 120 times the cosine of 30. Make sure you're in degree mode. And if we do that correctly, we get about 104 newtons. And if we do 120 times the sine of 30, that turns out to be 60 newtons. So 104 plus 60 adds up to 120. You say, Whoa, no, it doesn't. It has up to 164. But you're forgetting that the x and the y are at right angles. So if we apply Pythagorean theorem, 104 squared plus 60 squared, and take the square root of that, sure enough, we will get 120. You might want to check that out for yourself. Okay, now we can answer the question. Will he succeed in moving the crate? And the answer is yes, because 104 newtons is greater than 90 newtons. Okay, so don't make the mistake of just saying 120 is greater than 90 and we're all good to go. All right, three other questions that we can ask and answer. What will be the acceleration of the crate? Okay, so we're assuming the acceleration is in the x direction. That's what Stinky's trying to do. So the acceleration in the x direction is going to be the net force in the x direction divided by the inertia of the crate. Well, what is our x direction net force? Well, let's look at our force diagram. I've got 90 here to the left, and this is 104 to the right. This is 60 up, and this is 120. So which one of these do I use? The 120, the 60, 104? I'm hoping that it's pretty clear to you that we would use the 104. In other words, we do Tx minus the force of friction is going to be our net force, and all divided by the mass. Now we substitute in numbers. We have 104 newtons minus 90 newtons divided by a mass. I forgot what our mass was. 50 kilograms. Okay, so this is 14 divided by 50, which I believe is 0.28 meters per second squared. Okay, so look that over. Make sure that you're comfortable with what we just did there. Oh, I'm sorry, I made a mistake. Oh. Yep, that's good. Next question. What is the value of the normal force? Okay, this is a problem that always gives us trouble, especially in the last quiz. The tendency is to want to say the normal force equals the weight, but that's only true if we're on a flat surface, which we are. If we're not accelerating vertically, we're not. And if there's no other vertical forces acting on a crate. There's the rub. There is another vertical force, namely the y component of the tension. So if I look very carefully at all my vertical arrows, I see that I have two of them up. So the two that are up are the normal force and the y component of the tension. And that's got to be balanced by the force of gravity. Okay, so that's how I set up the next one. Because the acceleration is 0, those two have to be equal to one another. How can I do this without losing my view? Well, I'll just have to wing it. Okay, so the normal force, if I solve this, or plus Ty, so normal force plus Ty, so Ty we found out to be 60 newtons, equals m, the weight, and the weight is m times g. So I've got the normal force plus 60 equals 50 kilograms times 9.8 newtons per kilogram. Okay, so 50 times 9.8, I believe, is 490. So, solving for this, the normal force equals 490 minus 60, or 430 newtons. Okay, and that should make sense. The floor is not fully supporting the whole weight of the box because some of it is being lifted up by Stinky. Okay, if he were to pull horizontally, then that 60 newtons would go away, and then the normal force would shoot up to match the weight. Last question. What minimum force is needed to lift it off the ground at this angle? Ooh, this is a tougher little problem. Okay, so if I want to lift it off the ground, actually I'm going to just redraw it down here. Okay, so let's do a quick little diagram. I've got the weight of 490 down, and we're pulling at some angle of 30 degrees. I need to have a force that is in the y direction that's at least 490. So that's how I start this. The vertical component of the tension has to be at least 490 newtons, and it will lift off the ground. We saw earlier that I'm looking for T to solve for. So I want to know what is the minimum force. That's T. So what do I know about T and Ty? I know that Ty equals T sine theta. We did that way earlier. Now I can plug in the numbers. So I know that Ty has got to be 490 that's got to equal T times the sine of 30 degrees because we're still at the 30-degree angle. So if I solve for T, I see that T, the tension, is 490 divided by sine of 30. Sine of 30 is a half, so 490 divided by half is double 490, or 980 newtons. Okay, so this last problem, we just reversed what we did right up here. Okay, so if I want to lift the crate up, I need a vertical force equal to the weight. That's this one. So that determines how much I've got to pull here because some of it's going to be horizontal. All right, we'll do more practice with this in class, and this will also apply to the lab that we